Isolated systems. With conservative internal forces. And what I want to look at is what's known as a pendulum. So we've got some fixed point. So is there a problem? Okay. So we've got some fixed point over there. We've got a cable or a string, and to that string we tie a mass. And this cable is drawn out a certain angle from the vertical. And we know here the velocity of this mass is 0. And we let this mass go. So what happens is this mass will simply swing towards the vertical. So at some later point, the mass will be somewhere over there. And it will be moving in that direction. And we want to know what is the final velocity of the mass. So the mass moves along that trajectory. And we know that this rope or cable has got a certain length. So this is the type of problem we can solve using the conservation of energy, because if you look at the angle between the tension in this cable, so if I draw a free body diagram of this mass at this instant, the tension in the cable is pointing somewhere in that direction, and we've got the weight of the mass pointing down. If I draw a free body diagram of the mass over there, I've got tension pointing straight upwards and the mass pointing straight down. So the angle between the tension and the weight changes with time, and that makes this problem difficult to solve using Newton's second law. So we want to figure out what will the final velocity be when the mass is at the lowest point that it can be. And let's put in some numbers to this. So let's say the mass is equals to 0.5 kilograms. Let's say this initial angle is 5 degrees. And let's say the length of the cable or the string is equals to 2 meters. Right, so just to make it less abstract, let's use some actual numbers to calculate it. Now, if we analyze this problem, initially we know that if the mass has got 0 velocity over there, but it's a certain distance away from its lowest position, it will have kinetic energy equals to 0. And if this is our height, let's do it more generally. Let's just say this is its initial position. And let's say the surface of the Earth is somewhere over there. So this is its position above the surface of the Earth is y initial. So its potential energy initially would be m times g times y initial. So it's got no kinetic energy, only potential energy. Let's say here it is at some position y final with respect to the surface of the Earth. So its kinetic energy will be a half mv final squared. We don't know what mv final is yet. And its potential energy at this point we can say technically, if it's so high above the surface of the Earth, we can say that. You will see that it doesn't matter, because that is the lowest this object can go. So it cannot move lower than that point. So in that sense, this is like the baseline potential energy it can have, the lowest potential energy it can have. So we can effectively make that 0. But I'm going to do it more generally, and you'll see it cancels out anyway. Okay, so let's try to solve this. Firstly, we need to figure out if we look at that height, let's call this distance over there d. And let's call, we know this distance over there, that's just the length of the string, that's 2 meters. So if we look at this diagram, we see that y initial plus d, so that length plus that length, is equals to y final plus 2 meters. Right, so that's we can make that we can write that equation down. Now we can actually calculate d. If we look at this triangle, so the one that I'm coloring in there, d is the angle, is the side adjacent to our angle theta. So we can actually write d as being L cosine of theta, which is 5 degrees. So just using trigonometry. So this is then equals to 2 meters times the cosine of 5 degrees, which is 1.99 meters. So we can say if we substitute this in, we get y initial is equals to y final plus 2 meters minus d, which is minus 1.99 meters. So it's equals to y final plus 0.01 meters. So we can relate y initial and y final to one another through just the way we set up this problem. And this allows us now to calculate both the initial and final potential energies. So the initial potential energy, we said, is equals to m times g times y initial. So m times g times y initial. So this will be 0.5 kgs times 9.8 meters per second squared. And we've got y initial, it's equals to y final plus 0.01 meters. And we can say that, well, the final potential energy is equals to mg times y final. This is equals to 0.5 kgs times 9.8 meters per second squared times whatever y final is. So we can already now calculate the difference between the initial and final potential energies. So the final potential energy minus the initial potential energy is this minus that. So here we've got 0.5 times 9.8 times y final. We subtract 0.5 times 9.8 times y final. So those two terms will cancel, and what we're left with is 0.5 kgs times 9.8 meters per second times 0.01 meters. And the number you get if you calculate that, this is, let me see, this is equals to 0.049 joules, if I'm not mistaken. You can just check me out with your calculators. But yeah, 0.5 times 9.8 will be 4.9 times 0.01 is 0.049 joules. So we've calculated the change in potential energy, and we also actually know something about the change in kinetic energy. We know that if I take the final kinetic energy minus the initial kinetic energy, this is a half m times v final squared minus, initially, this mass is at rest, so it's got no kinetic energy. So this is just simply a half mv final squared. But we also know that if at any time I add the potential energy plus the kinetic energy, because it is an isolated system with only internal forces, this sum must give me the mechanical energy, and it must be equals to the potential energy at a later time plus the kinetic energy at a later time. And that number m must always be the same. It's not allowed to change. So we can write this as, this means that U final minus U initial plus kinetic energy final minus kinetic energy initial is equals to 0. Right? And we know this, we know that, we know this. So the only thing we need to calculate is the final kinetic energy. So I'm just going to do it over here where I still have space. So we get that the final kinetic energy is equals to the negative of the final potential energy minus the initial potential energy and plus K initial, but we know this is equals to 0. We've already calculated this. So, sorry, this is actually, I think I made a sign mistake here. Yeah, sorry, this should be a negative because we're subtracting this from, well, subtracting this from that. So if I subtract this from that, I get this negative. So all that this says is the final potential energy is less than the initial potential energy, which makes sense because initially this mass was higher above the surface of the Earth than it was finally. So that is then equals to negative 0.049 joules. So our final kinetic energy is 0.049 joules. This must be equals to, if I want to calculate the final velocity, so the final velocity is equals to the square root of 2 times the kinetic energy divided by the mass. That's just if I write that. So I know kinetic energy is equals to this. If I solve for this speed, I just get that equation. And if you plug in all the numbers, you find that the final velocity is 0.44 meters per second.